let us finish this course by a last chapter on a differential consonant. So let us consider the case S, and we say that f is differentially algebraic if and only if there exists n, an integer, non-zero polynomial having coefficient such that vanish f and its derivative. So in other words, you have a differential algebraic relation. And if the differential equation is linear, we say that f is holonomic. If f is not differentially algebraic, f is differentially transcendental. So I said that I consider the case S, but in fact it can be done in any field where you can derivate. So to simplify, let me consider f, which is a formal series. So f, which is a formal Laurent series, or homomorphic function of whatever you want. You need to be able to take the inverse and to derivate. So it gives a new element in a class of functions. So for instance, C of Z is included in the set of holonomic function. But it's also included in the set of a differentially algebraic function. So for instance, in a set of holomorphic function, you have exponential of x, and one example of a differential algebraic function is the p-Verge class function. So using a difference Galois theory, it has been proved that there are very few elements that are in fact differential algebraic. So the stress is one of the only ones that we know, and we're able to prove this. So the goal of this section is so the moral of this story is that there are very few elements that are differential algebraic. The element used to be differentiated in some time. So let me give this result due to order that gamma is differentiated on some time. So I remind that gamma is a function that is satisfied this functional equation. So let me admit the following lemma. So the set of differentially algebraic function is a field stable by derivation. So the reason why we're interested in this set of differential algebraic function is that you have a structure of field meaning that the inverse of a differential algebraic function is still a differential algebraic function. It's not the case for the holonomic function. If you consider the inverse of an holonomic function, it's not necessarily an holonomic function. So for instance, 1 over exponential of x plus exponential of minus x is not holonomic. So, so I will admit this lemma, and it suffices to show that gamma prime over gamma is differentiable on some time. I use this theorem. So why I'm considering this decision variable is due to the following fact. So sigma commutes with the derivation. So sorry. So it's equals to gamma prime of x plus 1 over gamma of x plus 1. And now I use the functional equation. So it's x gamma x prime over x gamma x. And now let me differentiate the numerator. So it's 1 over x plus gamma prime over gamma. So in other words, we prove that you have sigma f equals f plus 1 over x. So we have transformed rank 1 equation by an affine equation. And we can differentiate in both sides, and we find that the k derivative of f, we just have to differentiate k time. So we find x over k minus 1 for k plus 1 and k factorial. So the k derivative of f satisfies equation of the same form. Okay, so it's the reason why we make this change of variable. So to the contrary, assume that f, which is the n derivative of x, are algebraically dependent with n fixed. The solution of a system of this form so, and the di are 2 by 2 apart triangular matrices. So this term, let me denote it by ak. And a fundamental solution is given by diagonal of ui and I equals 1f and f to the power I. So let me call this matrix Q. So a fundamental solution, the Picard ratio extension, is given by R, which equals to C of X, U1 over determinant of U, that you quotient by I maximal sigma ideal. Let Ji be the image of Fi, which remind that is the E derivative inside R. So since you quotient binomial, you just add relations. So Fe are algebraically dependent, implies that the Ji are algebraically dependent. Okay? So it means that the dimension generated of the vector space denoted by J1 until Jn over C of X is strictly smaller than n. Otherwise, there will be all algebraic independent. On the other side, the Galois group is contained in a group of this form. So with di belongs to C. So so you can see this in several ways. More simple, so the more straightforward is to apply the theorem of Gauss transformation that says that if your matrix is inside an algebraic group, then the Galois group is inside this algebraic group. So this is an algebraic group, so the Galois group is contained inside. And so this is an algebraic subgroup of n copies of the additive group. So it's not very clear to see the additive structure of this group, but let me give an example exercise with n equals 1. So let J be a subgroup, be an algebraic subgroup of 1, 1 alpha. Show that is stable under addition and opposite. And furthermore, show that either J equals the entire additive group, so it's a structure of additive group, either J is just the identity matrix, so the group with one element. So the same kind of result for other n equation, for other n group, says that J is a proper subgroup of n copies of the additive group. If and only if there exists C1 until Cn c'est with T coming from 1 to K such that so sorry, let me write it differently and in a more simple way. Such that J is included in the subset of elements that vanish this vector. So it tells the structure of vector space. And the Ci are not R0. So remind that the dimension of the Galois group the dimension of the Galois group seen as an algebraic group over C equals to the dimension of the total Picard ratio extension which equals to the dimension of f1 until fn over C of x to the dimension of this, and we have seen that strictly smaller than n. So the Galois group has dimension strictly smaller than n. So it means that Galois group is a proper subgroup of n copies of the additive group. Okay, so now I use the lemma, the parameter, so that C1 complex number, not R0. As in the lemma. So let y equals to the sum of C1 times gi. And now I'm going to compute sigma of this thing. So it's equals to so sorry, it's not what I want to do. So let's see in the Galois group, and I want to compute the image psi of y. So I use the structure of ring automorphism. And so it's equals to CI plus CI di. With sum of CI di equals 0, because J is included with this set in this group. So it implies that psi of y equals 1. So Galois correspondence implies that J is a rational function. That y is a rational function. So on the other hand, sigma of y, so it's equals to Ci sigma of gi. So it's equals to sum of Cy minus 1 I plus 1. And so if you write expansion of y as a rational series at 0, as a rational function at 0, you can prove the following exercise. So there's a y here. So Ci minus 1 a plus 1 factorial I over xi plus y has no solution in C of x. So remind that the Ci are constants. So this is the main assumption that will be used to prove this exercise. And so we find a contradiction. And this completes the proof of the differential consonants of the gamma function. So to conclude this course, we have seen that the structure of a difference equation allows to understand what are the algebraic relations satisfied by a solution of an equation. We have attached to this group an algebraic group that measures the algebraic relation between the solutions. So the bigger is this group, less relation you have. And theoretically, compute the group allows you to compute the relation. And there are, in some example, there are algorithms to do that. Thank you very much.